Hello and welcome to our Orogenic Gold Exploration Workshop. In this workshop, we will take a look at the basics of orogenic gold exploration in greenstone belts. And this lecture forms part of a series of events looking into exploration techniques from a theoretical and a practical perspective. So in this workshop, we are primarily focusing on the genesis and practical exploration techniques of these kinds of deposits, and will then get all the basic knowledge that we require for working with data sets and real-life exploration scenarios. This lecture will be divided into 3 sub-lectures, and these will be available as 3 different videos respectively. So what's the agenda of this workshop? Well, first of all, I will introduce the relevance of orogenic gold deposits in greenstone belts. We will then talk about ore genesis and structural control, and then take a look at a number of examples from West Africa and Northern Europe to see the similarities of these controls on ore deposit mineralization and location. And last but not least, we will have an extensive session on the actual exploration techniques that are used in industry to find, locate, and evaluate such deposits. So let me quickly introduce you the background to this workshop, why we are actually having this workshop on orogenic gold exploration techniques. Well, first of all, I would like to say that orogenic gold deposits are fun. And that's because a number of different geological, mineralogical, geophysical, and geochemical techniques can be employed to investigate and explore them. And you will also very quickly see that these types of gold deposits, they are very, very similar all across the world. So whether you're working in West Africa, in Western Australia, in Canada, on these greenstone-hosted gold deposits, it will quite be a similar story all around. And as I just said, there are many different exploration techniques available and applicable. So whether you're interested in a holistic approach or whether you're a specialist geophysicist or geochemist, you will find that most of the techniques that are industry standard or that are currently being developed in R&D, they can be applied to this kind of mineralization style. Another important point I would like to make is that most workshops on orogenic gold, they primarily focus on ore genesis. That means you will have experts in orogenic gold who are presenting mainly how the ore deposits form and what the controls are. That is very, very important for all of us geologists, because if we don't understand how these deposits form, how then do we want to explore for these deposits? However, this workshop here is different as it adds the industrial exploration perspective, and I will spend a lot of time talking about the techniques that we need to explore these deposits. And that is really what counts in industry, that we geologists are able to squeeze out the most from the data that we can get, whether that's geochemical, geophysical, or mapping data. So as geologists, we are interested in finding new deposits and generate a healthy exploration pipeline for companies. That's why we need to know the best of both worlds. We need to know the important academic background of how these deposits form, and we also need to know how the techniques work that can actually give us that pipeline that companies need to have a sustainable exploration venture. So the focus of this workshop, after this introduction to these orogenic gold deposits, will be to practically crunch large data sets, look into the interpretation of geophysical and geochemical data sets, and use this data to generate exploration targets. So areas where we could proceed further exploration, whether that is new sampling campaigns or designing drill targets and testing these with reverse circulation or diamond drill rigs. So you will leave this workshop with skills that you can apply to your own data sets and improve your own exploration targeting and data interpretation workflows. Let's move on to the different gold deposit styles that we geologists know. Well, there are many different ways gold deposits can form, and you should have heard about all the porphyry copper, gold, and epithermal and placer deposits and greenstone-hosted deposits before. I'm just showing this slide here to make you aware in which different environments gold deposits can actually occur. There has been lots of research going into understanding the different controls, the different localities, the different geographical locations where these deposits occur, and we shall review these controls now in terms of the greenstone-hosted deposits. What we can see first of all is that gold deposits are always related to two important aspects. The first aspect is we have a large intrusion nearby. Whether that is with the intrusion-related clans or with the greenstone-hosted clans, there's always an intrusion which acts as a heat source to drive regional fluid flow. And in order to get a metallic mineral deposit, we always need to have this fluid flow available. We also see that most of these deposits are structurally controlled, and it particularly applies to the greenstone-hosted deposits. There's almost all the time a shear zone or a structural trend involved that controls mineralization. But also these gold deposit types, they have a distinct lithological control. In the greenstone clans, that is usually a green schist metamorphosed volcanic clastic sequence in a greenstone belt. And with the epithermals, you've got characteristic young volcanics on volcanic belts with deeper seated intrusion related gold deposits such as porphyry copper gold and other stockwork or skarn deposits. You have the control of porphyry type rocks that are intruding into a sedimentary or metasedimentary country rock sequence. If we move on to the worldwide distribution of greenstone belts and greenstone-hosted deposits, we can notice a number of interesting coincidences. It's very obvious that the big clusters of orogenic gold deposits can be found in Western Australia, in West Africa, in the northern part of South America, such as the Guyana Shield, in Canada. And what is interesting here is that these greenstone-hosted gold deposits, they can be found either in the Proterozoic or in the Archean geological time frame. Important to mention also is that this map is dated 2007. So all the recently discovered gold deposits in the Northern European area, such as in Finland and in Norway, have not been put on this map yet. Over the last 10 years, deposits have been discovered in other frontier areas of the world. So our first observation on this control of greenstone-hosted gold deposits is that these mineralization sequences and types, they occur in old rocks that belong to the Archean or to the Proterozoic, that are usually older than 1.5 billion years. So knowing this will already help us to define areas across the world that can be prospective. You can also see that there are much more Archean and Proterozoic terrains across the world that do not have any discovered gold deposits yet. For example, take a look at South America, in the central part of Brazil, or the northern part of Canada, Europe I mentioned, parts of Central Africa. Now, it doesn't mean that there are no gold deposits in these areas. It just means that these places have been completely underexplored. And for that reason, there exists still considerable exploration potential to find new deposits of this mineralization style. However, we do not need necessarily Precambrian rocks to form orogenic gold deposits, and we're going to take a look into this in a minute. So usually greenstone-hosted gold deposits, these orogenic greenstone-hosted gold deposits, they form in the Precambrian. However, if we take a look at the, for example, shale and wacke-hosted metasedimentary deposits that occur, for example, in Northern Ireland or in Scotland along the Caledonian Front, we recognize that these rocks are of a Paleozoic age, right? They are still classified as an orogenic gold deposit because they are related to collisional plate tectonics, okay? But in this workshop, we will exclusively focus on greenstone-hosted orogenic gold deposits. If we take a look at the grade and tonnage of these greenstone-hosted gold deposits, we can see a number of interesting and comparable facts across Canada in this example. So on the left-hand side, you see a chart that compares the grade and the tonnage of Canadian orogenic gold deposits and world-class, worldwide orogenic gold deposits larger than 30 tons. And we can see that most of the deposits that are known and that are in production in Canada have grades that are at least larger than 1 gram a ton and usually range between 1 to about 50 grams a ton overall grade. The tonnage, however, is quite variable and can range between 0.1 to 1,000 million tons. Of course, such high tonnage deposits usually have a lower grade, such as the Golden Mile deposit in Australia. The higher the grade you get, usually the smaller the deposit is. However, there are clearly some deposits in Timmins, for example, the Hollinger-McIntyre deposit, which has quite a high grade of 10 grams a ton and still has quite a large resource base and tonnage. This is a good chart that you can compare other deposits against. And if you're working on evaluating such an orogenic gold deposit, it's always important to know where such a deposit is actually fitting within the bigger picture, within the worldwide distribution of gold deposits. On the right-hand side, you can see the number of deposits against the ore tonnage and the ore grade. And it's very, very obvious that in terms of the ore tonnage, you have many deposits that are less than 5 million tons large. And you have less deposits, less and less, that actually have these bonanza grades and tonnages that are larger than, say, 20 million tons of ore. And this curve is quite significant. It's quite characteristic of the greenstone belt. It also gives you an indication what to expect when you go exploring in greenstone belts. So you will more likely find smaller deposits than finding quite a large-scale deposit available. That probably has quite a large footprint in terms of the geochemical and geophysical signatures. In terms of ore grade, it's a very similar story. The bonanza grade deposits, which have an average of 40 grams a ton, they are not very many. However, smaller grade deposits, they are quite abundant. And if you combine this knowledge with the graph on the left, you can get the picture that most of the deposits we are exploring for are somewhere in an average grade and tonnage, so somewhere between 5 to 10 grams a ton and perhaps less than 30 million tons of ore. However, I need to mention that the graphs on the right-hand side, they at the moment do not really exist for frontier greenstone belts, such as the greenstone belts in Northern Europe. There are numerous belts present in Finland and Norway. We've got the Central Lapland Greenstone Belt, we've got the Karasjok Greenstone Belt in Norway, and the Kautokeino Greenstone Belt in Norway as well. And whilst the Central Lapland Greenstone Belt is currently, as in 2020, heavily explored, the aforementioned Norwegian greenstone belts have received very little attention, and there are maximum 1 or 2 mineral deposits known in this greenstone belt. So this will be quite a skewed curve in these areas, in these greenstone belts, if you compare it to the two graphs on this slide here. If we take a look at the orogenic gold deposit clans, let's talk a bit about the geological setting and key signatures. I've mentioned before that you have within the orogenic clan different deposit types. You've got the Greenstone-hosted deposits, usually in the Archean and in the Proterozoic. You've got the turbidite-hosted veins, which are usually in Paleozoic sediments or metamorphosed sediments. And you've got BIF-hosted gold deposits. They can also be found in greenstone belts, as we will see. But what makes them very similar is that both on a regional to local scale, they are controlled by structures, and those are largely shear zones and fold zones. All of these deposits, they have this structural control, and we need to remember that structural control is, as we see, the most important controlling factor on orogenic gold mineralization. Without these regional and local shear zones, folds, and antiforms and synforms, we cannot move fluids that are then trapped and form a gold deposits. Equally, we need at both regional and local scale a typical sequence of rocks to be able to form a chemical barrier that allows the gold ions that are usually complex in hydrothermal solutions to drop out and form gold deposits. Now, those lithologies are usually volcanosedimentary rocks. They can be conglomeratic rocks, and also these deposits are related often to intrusions that it forms the heat driver of these hydrothermal fluids. Now, why are these lithologies, especially the volcanoclastic sediments, so important? Well, they first of all form rheological heterogeneities, meaning you've got competent and incompetent rocks. And if you have competent rocks, they can break easy during brittle deformation. You also have iron and sulfur-rich lithologies such as basalts, tholeiites, or graphitic schists, and they will basically enhance the chemical reactions that rob sulfur from the gold ion complexes and will then free the gold ions, and in a redox zone enable the gold to precipitate and accumulate. Also, what we need to understand, and I will talk about this in more detail later, is that we need also evidence of alteration zones. And alterations such as carbonate alteration, sericite alteration, presence of sulfides. And that is important because this alteration will enhance the competency of rock sequences, which will, as we just heard, which will increase the ability to fracture and break and form additional late-stage fault zones in a greenstone belt. So that as just an overview of the key geological settings and signatures that we need to find when we're exploring for gold deposits. And I will now go into more detail explaining these criteria in detail. So as I mentioned before, structural control is the single most important factor controlling the distribution of orogenic lode gold deposits and the geometry of ore chutes. If we take a look at a regional map, and this is a map from Northern Ontario along the Timmins Gold Trend, we can see that most of these gold deposits hosted in greenstone belts, they are located along large regional fault zones and, to be more precise, largely shear zones. And that is not a coincidence. The fact that we need shear zones in greenstone belts will enable our mineralization system to provide space to have these hydrothermal fluids migrating through the crust along these weakness zones and then deposit in areas that show a favorable composition of volcanosedimentary units in the greenstone belt. And what we usually find is that we have quite a very, very complex structural development of these greenstone belts. And here it is important to understand the different deformational phases that can be observed in such greenstone belts. Very often, orogenic gold deposits form during the later stages of the structural and tectonic development of such a greenstone belt. Whilst in the earlier deformational phases, for example, D1 or D2, you have regional alteration, you have thrusting, you have the development of early structures. This is not necessarily when gold is emplaced. Only later, usually during the third or the fourth deformational stage, when you have already large volumes of hydrothermal fluids pumped through the greenstone belt and you have regional alteration produced that are then further compartmentalizing the structures and the domains you already have, only then usually you will find that this late stage syn to post-orogenic events will lead to the formation of orogenic gold deposits. So the message to take away here is that we need to understand the regional geology first and foremost. We need to understand what deformational phases have happened in a greenstone belt. We need to be able to identify these in geological and geophysical maps. I have posted in here another interesting overview map of gold deposits in the Norwegian greenstone belts. Remember, I mentioned earlier that these greenstone belts in Norway, they're heavily underexplored. It's been known for many decades that there are greenstone belts in this area that are extensions of the Finnish greenstone belts, but there is largely a problem with community access and with glacial till that have to date prevented gold exploration in this area. However, coming back to the point about structural control, these deposits have been identified there. They are very clearly following structural trends. And you can see that this area is quite heavily deformed. You've got multiple stages of northwest, southeast trending shear zones. You've got jogs and bends in these shear zones, and if these shear zones are formed in competent rocks, then these bends and these jogs will enable the rock to break during brittle deformation and establish then further fold trends, in this case northeast southwest trending folds that are then cutting up the already deformed area a lot more. We can also see that these known mineral occurrences are exactly located at the intersect between earlier shear zones and later stage deformational events. If we zoom into these deposits, into these mineral occurrences more, we can then see that lots of folding has happened during earlier deformational events. You can see synclines and anticlines being cross-cut and deformed by shear zones once more. We can see the importance of granitic intrusions as heat drivers for regional fluid flow, but also enhancing the contrast between the rheologies of competent and incompetent rocks. And on the bottom left is a summary sketch through the Bityo-Vage deposit. You can see that the mineralization is largely related to trap structures such as truncated folds and also shear zones that are cutting up these earlier stage folds. So being aware of how structures control orogenic gold deposits in greenstone belts is absolute key, and we need to understand this at regional scale, so the top left figure, and also at local scale, the bottom left figure. So these regional and local scale controls are absolutely essential in understanding the location and exploration potential of these greenstone belts. Moving on, if we take a look more at the microscale deformational structures present in orogenic gold deposits. So for example, if we go underground and study these veins in more detail, we can see that the typical structural geology and the deformational characteristics are similar at small scale or at micro scale to these characteristics observed at regional scale. So there is a transferability and a scalability of the structural geology in this case. For example, typically in these shear zones, we will find textbook-like en echelon tension gashes. We will find different deformational stages of veins and of folds. We find early formed and later formed veins, and understanding these at microscale will of course help us to understand the bigger picture. However, usually in exploration we start with a bigger picture. We start with a land package that we are exploring. So it's important that we go back to our basic structural geology knowledge. And I promise you that these micro structural features that you see here on the slide, you can sometimes even see these in geophysical images such as magnetic surveys. And that is the exciting part of exploration that I really enjoy, that we can apply the scalability of such observations all across different geological and geophysical data sets. To put a bit more color and figures into the game, I'm just showing you here a number of typical fold, fill, and extensional veins that can be seen in these orogenic gold deposit styles. Those are photos taken largely underground, and these veins are usually characterized by moderately to steeply dipping laminated fold-fill quartz carbonate, and that's important, quartz carbonate veins in brittle to ductile shear zones. These quartz vein textures, they usually vary according to the nature of the host structure. So depending on the structural type you're looking into, you could have extensional or compressional structures. You see up there on this figure, boudins, quite a vein that's been boudinaged. You can also see, of course, en echelon tension gushes. It really depends on the local stress fields and the structures that are produced. For example, these extensional veins, they can typically display quartz and carbonate fibers, usually at high angles to the vein walls. And of course, they also feature multiple stages of mineral growth. And that is something that you can recognize when you go and do your basic geological observations, okay? And measuring these veins in detail and then producing your stereo plots, they will really help to figure out not only how many generations of veins do we have in a deposit or in an area, but it will also tell you the directions of stress that formed these veins. Importantly, if you understand the direction of stress and the nature of the deformation that's been taking place, then you can reconstruct the regional stress and deformational axes that have led to these gold deposits formed at micro and at a regional scale. And that's the very important point I would like to make. Whether it is that you go into the field and record structures underground in a tunnel or in an outcrop, or whether you look into regional airborne geophysical data sets, always think about what kind of stress directions do we have and what does it tell us about the different deformational phases. The dimensions of these veins can reach thicknesses of centimeters up to 5 meters, and it can extend in length from 10 to about 1,000 meters. The vertical extent can be greater than 1 kilometer to 2.5 kilometers. Usually, as I said, those veins are moderately to subvertically dipping. They form usually underground mining targets because of their steep dip. Let's move on to lithological controls and understand why different lithologies have an impact on the location of these mineral deposits. We know already that gold is deposited in numerous types of structures. We talked about earlier the shear zones forming jogs and bends and then forming dilational spaces if you have the interaction or the reactivation of older type of structures and you have the interaction of younger and older structures that forms dilational zones. However, what we need to pay particular attention to is that these deposits, they form in low tensile strength lithologies. Or in other words, you need competent rocks that can fracture and that can then enable the formation or the reactivation of older faults. Now, not all rock types are competent, and that's why we need to look a bit more into detail what the different volcaniclastic rocks actually do that enhance the prospectivity for orogenic gold deposits in greenstone belts. If you take, for example, a few chemical formula to illustrate how hydrothermal fluids react with rocks, we can observe that usually gold is transported, or I need to better say gold ions are transported in complexes, okay? And these complexes, they could be chlorine complexes, these complexes are destabilized if you have your hydrothermal fluids interacting with iron-rich rocks, such as basalts, such as iron-rich basalts or tholeiites, because these rocks, they will rob, if you like, the iron and the sulfur from these chemical complexes that hold the gold. So in this case, in the first equation, you've got siderite, it's an iron carbonate. If that reacts with H2S and oxygen, it will form pyrite, CO2, and water. Or in the next equation, if you have siderite reacting with the gold-bearing sulfur complex, you will rob that sulfur out so that you can form pyrite from siderite. You form CO2, H2O, and free gold. So that means that your gold complex is destabilized in the fluid, and you get gold that you can precipitate. And for that, we need to have these iron-rich and sulfur-rich lithologies, such as tholeiites or graphitic schist. And that, of course, also forms a redox barrier. If you have quite a reduced rock, such as a graphitic schist, your hydrothermal fluids, they will hit that barrier and form sulfide along with gold. And what's very important here is that you have what's called the ground preparation phase. And ground preparation is usually regional or local alteration by hydrothermal fluids that have circulated the rock and the rock succession during previous deformational phases and left a carbonatization or albertization overprint on the rocks. So not only do you need to have iron or sulfur-rich rocks, you also need to have them ground prepared beforehand by regional alteration, because this will help to increase the competence of these host rocks that we've just been talking about and allow the formation of late-stage faults that perhaps interact with your old structures, perhaps reactivate them or form dilational zones. And this interplay between structure and lithology is absolute key in the formation of these gold deposits. I've talked already about these basalts and these tholeiites and BIFs as well, but why again are these important rocks that form a lithological control on these ore deposits? Well, as we said, if you have reduced auriferous fluid reacting with iron-rich rocks, it triggers the precipitation of gold. We've already seen this in the last slide. Iron-rich rocks also have different strengths compared to surrounding lithologies, and that provides us with the competency contrast that we need and that I've been talking about. One of the reasons for that is that these lithologies, they can influence the deformation and fluid pathways in adjacent units. Let's go back to the first example we talked about in Ontario, in the Timmins area. The gold deposits there are hosted in metasediments such as turbidites or gray rockies, immediately adjacent to mafic and ultramafic volcanics. So this is nicely fitting into the scheme that we've discussed over the last 10 minutes or so. In central Lapland, we will see this in a few more examples later on. Gold deposits, they are usually hosted in tholeiitic basalts and graphitic schist, but also in conglomeratic rocks that form along these bends and jogs of these shear zones. So we can see wherever you go into the world, into these greenstone belts, usually structural control and lithological control, they are very, very similar. I mentioned the alteration and the ground preparation that is required before. I just wanted to give you another example of this. In that photo that you can see on the right-hand side, I've been up in northern Finland along the Hanimaa shear zone. There are a number of trenches that expose the bedrock, and these trenches have been constructed across a shear zone. Now, if you take a look at this rock, it is very difficult and challenging to actually say and determine what that rock actually is. And that's because that rock has been completely altered. There is plenty of anchorite, iron-rich dolomite in there, quartz, sericite, chlorite. So this rock has really undergone a very painful time, as it's been completely altered by these hydrothermal fluids that have been pumped up and down this Hanima shear zone. That's why understanding and recognizing alteration control is very important when you're out in the field trying to investigate rocks and the alteration patterns. So the alteration I've just mentioned, dolomitization, carbonatization, sericitation, chloriticization, they're all a result of the introduction of potentially sulfur, CO2, K2O, H2O, and perhaps even include the introduction and remobilization of silica. So silicification is also a possible alteration feature in these areas. Okay, so we'll talk about this a bit later when I talk about exploration techniques, but I really want to draw your attention to these alteration controls that form the ground preparation for these orogenic gold deposits. Another important fact that you need to be aware of is the mineralogical control on these gold deposits. You may have heard before you can have free gold, but you can also have refractory gold. Refractory gold is hosted within sulfides. Now, the most ideal case, the most straightforward mineral processing scenario is if you have free gold, so gold that is not necessarily occurring within sulfides. And why is this very easy for processing? Well, you only have to crush and mill the rock to extract the gold. However, if you have refractory gold hosted in pyrite or even worse, arsenopyrite, then you have to undertake a lot more sophisticated chemical treatment and dissolution of this host mineral. And that can lead to environmental concerns. For example, the Kittilä mine in the Central Lapland Greenstone Belt, it's the only operating gold mine at the moment. That gold is predominantly hosted in arsenopyrite. Now, of course, you can imagine that if you process arsenopyrite, you liberate arsenic, which is not necessarily what you want for your environmental management. Nevertheless, this mine site has found ways to deal with this issue sustainably. Okay, so always be aware of the mineralogical controls, where the gold is hosted, whether the gold is free or in refractory state. If you have refractory gold, I just wanted to mention a few common metallurgical processes for your understanding. If you've got oxidized ore, you use processes such as heap leach or ammonium thiosulfate extraction, carbon and pulp or carbon and leach. Those are on a mineral processing plant usually large silos of chemicals that extract the finely milled gold from the other constituents in the liquid. You can also apply to sulfide ores, autoclaving or bioleaching to free the gold from the sulfide particles. But in essence, both types of ores, whether it's oxidized or sulfide ore, it requires roasting because of the carbon that's present, followed by the use of cyanide. And that, of course, also has environmental impacts. So let's go back and summarize the controls on ore deposits and mineralization. And really, if you understand and if you can explain these controls, then you'll be able to understand how these gold deposits work in the bigger picture and how we can use it in exploration. So first of all, we need to have the metamorphism ingredient. We need regional green schist metamorphism of a volcanic clastic sequence. We need to have the basalts metamorphosed. We need to have the sedimentary rocks metamorphosed, and we need to usually encounter these typical alteration mineralogy, chloride, perhaps epidote, that really give the rock often a greenish appearance. We need district scale jogs commonly associated with arrays of crossfolds that can accommodate the bending of competent units and in fact then facilitate the introduction of late stage folds. We need anticlinal fold hinges and limbs that are often truncated by folds and shear zones, and which represent sites of brittle to ductile rock failure. Again, that's because we need these hydrothermal fluids to migrate along pathway in being trapped in structures so that they can accumulate and form a deposit. We also need to investigate and be aware of the boundaries between rigid pre to thin orogenic intrusions and ductile greenstone belt sequences, which are of course sites of inhomogeneous strain, and that will also trigger the structural controls, the lithological controls, and of course then ultimately the emplacement of gold deposits along these lithological and structural features. We need the presence of favorable lithologies, facilitating first of all the development of redox zones and the removal of gold complexes from the fluid. So we want to liberate the gold from the complex and have it precipitating as free gold ideally. Now those lithologies that we need are usually iron-rich basalts, tholeiites, banded iron formations, and graphitic schists. As a reminder, these lithologies, they rob the complexes of, for example, sulfur and iron and liberate the gold. We also need to ensure that we can trace and follow regional fluid flow and circulation along with the presence of heat sources, and that is usually a result of syn and post-orogenic granites that drive a mineralization system and enable then during later deformational phases the introduction of hydrothermal fluids into these favorable lithologies. So I would like to conclude this session here. As a summary, we talked about the specifics of orogenic gold deposits. We looked into the global distribution, and we looked into the major controls, whether they are structural, metamorphism, or lithological controls that we need on both a regional and a local scale to emplace gold deposits and into a volcanosedimentary sequence in a greenstone belt. In the next session, in the next video, we are then going to take a look a bit more into some prominent greenstone belts and see how we can apply this knowledge we learned today in a practical setting in a greenstone belt, and we can see how comparable these controls are across different belts and across the world. Thank you for listening in.